I'm gonna go ahead and get started with these problems here. We're continuing our discussion though with what we talked about last week. We kind of finished up a quick review of some different things as far as the algebra is concerned, solving different equations, graphing, and we led into discussing limits, right? And limits is definitely an important concept when we start looking into the calculus of numbers, all right? The limits is definitely an important foundation because with limits, this is where we define a lot of the things that we're going to work with this semester. So it's very important that as we go through limits, that we get a strong foundation and that we're comfortable with working with them. The one thing that I will remind you is that remember, a limit is not the same as evaluating a function. So like here, if I wanted to go say, hey, what is f of 2? And I forgot, y'all remember last week. This is supposed to be have an equal sign here, sorry. But when we evaluate, we could say, hey, what is g of -2? That's plugging it in where it belongs and then working out to get to a value. Limits don't do that. Limits use information around that x value to help point to something, okay? It's more of a pointer than giving the exact value. Now, one thing we did see, if you remember last time, is that with some of our limits, we can get to something that we're not allowed to use. So that was kind of where I started here. We talked about how, hey, I can't plug in 3 because it puts a 0 in the denominator of this rational function. But that limit allows me to still point to that value. Okay. With that said, all right, what would you say the limit as x approaches -2 from the left-hand side, that's what that little superscript stands for, of our function g of x? Right? So nice thing here is we have the graph, right? So if we look at all these points here, does everyone agree to point with that value of 4? Is there any concerns with where I'm getting the 4 from? All right. So as you follow the line here, where's that y value? It's at 4. That's what we're looking at. Now remember, what we're saying is, hey, we're focused on x equal to 3. I mean -2, sorry. We're focused on x equals -2. We're not plugging in -2. What we're doing is we're looking at the x values. Sorry. As we go along the x-axis to -2, right? What are the y values doing? So that's from the left-hand side, right? It's very important that we see which side we're working on here, okay? The nice thing is with a graph, like as I was mentioning, we can just follow the line here and see that it points to the value of 4. It doesn't actually get there because there's an open circle, right? We can't actually use that value, okay? But it's still the limit points to it. Does that help with that? It's coming from the left. That is exactly right. Now, what does the next limit ask us to look at? Coming from the right. We're saying, hey, what happens is I go from the right side now rather than the left side. Okay, so that's what we're seeing here when we say x approaches the -2 with the little plus sign, we're approaching from the right side. But this one, as mentioned, points to what? We come to with the 2 there. Now that one's a little bit different. So if I erase all this so we can see the original graph, what's here that's not up here? It's a closed circle, right? So like if we go plug in -2 on our function, well, hey, it does equal 2. So if we evaluate, we would get 2, but the limits, as we can see here, they're kind of different, right? And this is one of the important things that we want to see from limits, that, hey, when I take this perspective, we need to look at from the left-hand side and the right-hand side to see what they say. Well, if we try to talk about -2, what do the limits tell me? That the limit, when I take into consideration both sides, does it exist and have a value? Or does it not exist? It does not exist, right? Because 2 and 4 are different numbers, right? Does everyone agree with that? So here we would just put like D and E. Does not, oops, meant to write it out, sorry. If they're the same numbers, that's correct. And as I pointed out before, that the one we did Friday where we had 3 as a whole of the graph, even though we couldn't plug 3 into the function, the limit existed because it pointed to the same value from left and right, okay? Any questions, concerns with that? Now, what are some different ways we could have calculated this limit if I didn't have the graph? So if I go over here and I delete the graph, what are some different ways we could have calculated the limit right now? You could plug in, but a table approach would be the way we want to do that, right? Not actually plug in -2, but let's use values around -2 to see what happens as I get closer, right? Now here, this one's a little bit tougher since it's a piecewise function, right? So we couldn't necessarily jump to the direct substitution part. However, as long as you understand that this is your left-hand piece and this is your right-hand piece, we could have done a quick thing saying, hey, what's -2 plus 6? Well, hey, that's 4. Okay. We're not plugging into a function at that point. What we're doing is for limits. So we intentionally would pick this piece for the first limit because I'm coming from the left-hand side. Everyone follow that? Yep.
What is the left and right hand side based on the negative and plus sign?
Yes. So this is left-hand side whenever you see the negative, and this is the right-hand side whenever you see the plus sign. Now, what does this one not have? Right? It's just -2 without that. That means, hey, we're taking into consideration the whole picture, both sides. Now, with that said, look, would you say this graph is continuous or discontinuous? All right, where do you see a discontinuity at here? So if you were to follow the graph, could you stay in one line the whole time? Or do we have to change it at some point? We have to change it, right? So this right here is a discontinuity, and it would be what we call a jump discontinuity. We go from one point to another point, and then we continue on. All right, if we look at like a line, as we kind of talked about the other day, lines, their domain is all real numbers. That'd be an example of something that is continuous. We talked about quadratics, right? Then we graph one of those. That would be something where the domain's all real numbers. Hey, that would be a good example of what something that looks like that is continuous. Okay. Well, here's an example of a jump discontinuity. Okay. This would be a removable discontinuity, right? Different things to understand here. I could have put a whole random point here if we wanted to and wrote it like a piecewise function. Okay. So no, there's different things that we can look at there.
What is
Does not exist. The key to understand is since these were not the same, it doesn't, the limit doesn't exist. So if you wanted to write it out, it'd be like, hey, the limit does not exist. Just to make it quick though, we could just put D and E. Now, with that said, if your limit doesn't exist, is it continuous? No, right? When we look at limits, if the limit doesn't exist at a value, then we have some type of discontinuity, right? That's where different questions come in. Remember, we talked about rational graphs a little bit, how sometimes we could have an asymptote. That's one of the things we'll kind of briefly look at today as far as introduction there, of how to start looking at the continuity of a graph, or when there are discontinuities, what to do with them, okay? Here's another one we could look at real quick. Be careful to see here though, with our graph, the first list is all for -2, and the second list is all for +2, right? So keep that in mind. But we're gonna do the same thing we did before. Okay. Now I gave us the graph here instead of the function, but hopefully you're like imagining like, hey, this would be another one of those piecewise functions that we just looked at. The only difference is it'd be like x is less than or equal to x is greater than 2. That would be the change that takes place here. Okay. Now, with that said, as we look at this first one, right? What are we doing there? What is that asking me to look at? The left-hand side of -2, right? So this is our focus here. So what do all these values point to? All right. Do we all agree with one? It's kind of like, I like how another teacher put it. It's like you're going around, you're getting information, you're just kind of gathering some gossip to make a determination of what's going on. We're not actually talking to the point itself. We're using all that information around it. Thankfully, we could see the graph goes through that point though, right? That does help here. So we're all good with that first one being 1? Does it change then when I go to the right-hand side? Would you all agree that it's still pointing to one, even from the right-hand side? Huh? So as we go from the right-hand side, as we look at all these points here, what's it saying about that? Right? Well, remember, we're approaching -2. That's the whole point of the limit. What happens is we approach the -2 from the right-hand side. But we're using the points to make that conclusion. So the -2 is the X value. So what value should we be looking at? But the Y value, right, is kind of what we look at, right? The limit, it puts in the value that we tell it to. So in this case, hey, we're focusing on X value, so we're going to get a Y value back, okay? With that said, though, as mentioned, we're all good with Y it's 1. What would you conclude then about the limit as X approaches 2? So the limit exists, right? And we know the value is 1, okay? Make sure you see their kind of the wording's a little bit different. Hey, the limit as X approaches 2 exists, and it happens to be 1, okay? Now, another thing you can look at here, if we just call this function f, right? We're looking at f. What would f of -2 equal? 1. Do we all agree with that? Now, the reason I point that out is make sure, again, go back to that graph that we looked at here. What was h of 3? Did we plug in this value of 3 here? What did I put there on the graph? A hole, right? Remember, that came from us looking at this piece here, right? And saying, hey, I could simplify, yes, but I still got to keep that restriction, right? So understand that this would be a situation where I could do the limit, but I can't even plug into the function. Everyone follow me on that? Whereas what we just saw in that previous one, or the one we were just working on, I mean, hey, I actually can plug into it. Not only could I plug into it, what's special about the value we got here and the value we got here? They're the same, right? And this is the way mathematically we show that something is continuous at that value. So once you look at this, if you can show that the limit exists, right, and get that value, and that you can plug in the value as well, and those values are both the same. Another way to look at it is like the limit as X approaches A of f of A, not only does it exist, right, but it equals whatever you get when you plug in that value. Now, I'm using A to generalize it, but know that like for this one, we started with -2, right? At that point, we can now conclude that this graph is continuous at X equals to the -2, right? Oops, if I can spell continuous. Now, hopefully what you take from this is just us kind of going through and looking at the graph and seeing how the limits given. Make sure you compare that to what we looked at last week on Friday, is that one that had the hole in it to see the differences where, hey, the limit existed and I got the value of 6, but I couldn't plug in 3. I wasn't allowed to because of the rational functions restrictions. Whereas here, hey, that's a line that just happens to be part of a piecewise function, so I could plug in the -2 here and be perfectly fine, okay? Now, with that said, though, be defining something being continuous, you need to make sure to go through the steps, right? Usually you want to start off by first checking, can I plug the value? And that's usually because you could do that pretty quickly oftentimes. Just try to plug the value in, see what happens, right? After you do that, then look at your limits from the left-hand and right-hand side. Once you do both of those, compare the values you get. Right? If they're the same, then we know that the overall limit exists and we have the value that it should be. Lastly, compare the values you get. Are these the same or are they not? Right? If they are the same after you do all that, then you know that it's continuous. Okay? We follow me on that? This is more of an introduction. I just wanted you to show why one of the reasons we're doing all this. That's something we'll definitely have to work on, is determine if something is continuous. If not, what type of discontinuity is it? Will be another thing we look at, okay? Any questions though with approaching -2? All right. right? So one of those things to just know that as we go through this is talking about continuity of a graph, right? And good examples, if you want to know what continuity looks like, remember, go think of a line or think of a parabola, right? Graphing a quadratic. There's no breaks in it, just one solid line for all real numbers, okay? With that said, though, what changes when we go look at positive 2? All right, we can visually see what's going on here. Is it continuous? No, and that's one nice thing about having a graph. We can visually see that, like, hey, not really, there's no continuity here, right? This would be, again, hey, it's a jump discontinuity. Once I get here, I have to jump down and continue on, right? So with that said, though, what is the limit as we approach from the left side? Do we all agree with 3? All right, so if I go to the left side, remember here, we're saying as I focus on positive 2, sorry, I'm approaching from the left side right now. So I'm going along all these values to see what happens. Nice thing about a graph, I can visualize individual values, and all those values are pointing to that point there, right? Nice thing about it, hey, the y coordinate is 3. Now, as far as the function is concerned, that would be like, hey, I know I have to plug that one in there because it's a solid dot, but what we wanted is the fact that it points to it, okay? What about the right-hand side then? What do all these points point to? We're all in agreement with negative 2? So at this point, what would we say? The limit does not exist. And just for the sake of time, I'll just put D and E again, but just know like a proper way to write it out would be like the limit does not exist. You don't even have to write this entire statement, right? You could have just put, hey, the limit doesn't exist, okay? Now, as far as like looking at a textbook and a proper different definition of continuity, what you'll see is that they'll say like the limit as X approaches something exists and it equals this, right? Yep. What do you mean by on the left? This is the one, oops, sorry, thought I was with this. This is the one that tells us the direction. Yes, but understand the key is that's why I changed it right at this way. So we're not always going to have the same graph going on. I just use these as an example because I feel like it helps kind of get a clear picture of what happens when you're dealing with limits. So having that discontinuity, the key is first go find the value you're working with. So as we see here, it's like, hey, that's a positive 2 where this one was a negative 2, right? Then check to see if it's one-sided, right? Because the first ones I gave you one-sided, what it's telling you is like, hey, because this is here, I'm going to focus on these X values up to that value, right? That's how we know that, okay? Here, then you just happen to be like, oh, I use the line on the left because that follows what I'm doing, okay? The reason I pointed out like that, think about the square root of the square root function, right? So if I gave you like the square root of X plus 4, that graph would look like this. So there's nothing over here on the left. You could only do a one-sided limit at a certain number, right? The way I have it written, only you can't do anything over here. So there will be some situations where it's like, hey, I can't do this. So maybe I don't want to do this particular limit for that side. But let me check the other side. Does that help? Yep.
So in order for the limits to exist, the approaching from the left need to be equal, approaching from the right.
Yes. In order for the limit to exist, the left and right hand sides have to agree. Any other questions or concerns? So make sure you see here that the 2 points we focused on were positive 2 and negative 2, right? Here, the key was that my line jumps down to another spot. And so it's not continuous, okay? As I look at the negative 2, though, as I go from the left and the right to look at that particular point, I get a limit. So that's first, the limit exists. But also know that you can plug that in there because it is a point on the graph. It's a solid line. Okay. So whenever we're looking at the continuous aspect, first we have to show I can actually plug in that value. So that's why I'm saying, hey, we got a solid line, we could plug that value in. The next step then is to show that the limit exists. So that's what this piece would be here. Hopefully you're catching on that. Okay, I do left hand, I do right hand. If they're the same as mentioned, the limit exists, and that's the value I have. I don't have to do anything else. Just show that it exists. If these two things agree is what I wrote here. If the limit exists and the value is the same thing I get when I plug it into the function, then it is continuous at that value. That help with that? Now keep in mind, the only way for this to happen is the limit must exist, right? So that's why we go through that process. Now, again, I don't remember if you were in here when I went back to it. This would be a good example of I could do that work and it's not continuous, even though the limit exists. Right? Remember, this was a special case where I gave us a rational to begin with, but we were able to simplify it, which won't happen all the time. But through that simplification, that restriction doesn't necessarily show up in the graph if we're not careful. We have to put the hole there ourselves. Why we call it a hole. I had to go erase it and put a circle to show don't use that particular point. Okay. But as you'll see here, it's like, hey, I can do the left-hand limit and I can do the right-hand limit. They both equal 6, so the limit exists. But I'm not allowed to do this. This is not allowed because 3 would put 0 in the denominator of my original function. Does that help a little bit with that too? There's many different things too that you'll find that, like, as far as discussing functions, we often work with functions that you might be comfortable with, but as we bring in different types of functions, for instance, exponential functions is definitely something important to this course, right? As we deal with business, when you start thinking about money and savings and such, things grow exponentially oftentimes, right? Or we can use an exponential or logarithmic model. So sometimes having a limit helps us better understand something, okay? I think I quickly talked about it. When we look at an exponential, the graph looks something like this. But no, over here, this never actually got to whatever number we were approaching. That's why we called it a horizontal asymptote. Okay, something you might remember from college, your college algebra course. Okay, so this is where limits definitely help us go a little bit beyond what we were able to before. Now, these two, took a little bit different approach, right? Hopefully what you see here with these two, I didn't give us the graph. Here we have the function and we want to try to find the limit, okay? Now, understand there's different ways we can evaluate limits as we talked about today. We can use a table approach. We can look at it graphically. We can try direct substitution. And if those don't work, there's some other things that we can work through, but there's gonna be some things that we can't really do right now that we'll discuss as we go through the course, okay? But know right here, if I don't give you a graph, you could draw one if you want to, but that's probably gonna take more time than needed, okay? We could do a table if you're not comfortable with something, but before you do a table, just try direct substitution to see what happens. So this would be a situation where I'd go do a little side work real quick and say, hey, can I actually plug 5 into this function? Okay, let's try it. Now, hopefully you're seeing here, it's quadratic. So a quadratic, as we mentioned, the domain's all real numbers. So it should work nice. Okay. Now, also hear me as well. I'm doing this as side work because the limit isn't me evaluating the function. However, if we know this function kind of already, we know that it'll work nicely. This is where we can kind of use that and say, hey, let's just try the direct substitution, see what happens. The good news here is after we do that, we find that we do get a nice value. What is it going to be? 17? With that, we could just say, hey, by direct substitution, this limit's going to be 17. Okay. Know that direct substitution doesn't always work though. Okay, so, but I would always encourage you, try it first just to see what happens. Okay. Yep. That would be a good example. If I try to plug 3 here, what am I gonna get? Yeah, so that would be a good example. When would it direct substitution not work? I get 0 in the denominator. It's not defined mathematically, so I need to find another way. Now, there's other cases that come up as well, but that's just one example, okay? As you can see, though, what was the next problem I looked at? Another rational problem, right? Now, here's one thing. I plugged in kind of doing the long approach. Another thing that I would strongly encourage you, be comfortable with your synthetic division. All right. So as I deal with this, I think we would both all agree that right now we got 0 over something, right? 3 minus 3 is 0. Now, I'm not giving us the value right now, but we're just trying direct substitution. Is everyone good with that? Now, when you start dealing with polynomials like we have here in the denominator, the synthetic division is going to help you out a little bit, right? So I might write synthetic division a little bit different than you do. Use whatever you're comfortable with. But the idea is, hey, I'm working with 3, so I'm going to try to plug 3 in. The nice thing about synthetic division is we can use that and the remainder theorem to evaluate polynomial expressions. Okay. What that means is take your coefficients in the constant term from the polynomial, if you haven't seen it in a while. The terms are in descending order, so make sure you see that that lines up as far as x squared, x, and that constant term. And from here, it's just addition and multiplication, right? We can bring down the 1, right? The idea is like 1 plus 0, and then you will use multiplication. This is where we'll go and say, hey, what's 3 times 1? And with that, I'm going to bring it back above the bar and put the 3 there. Okay. So if you're below the bar, you multiply to get back up. Right? What do I do now? Now I add them together, right? What's negative 8 plus 3? Negative 5, right? Well, now I'm below the bar. To get back up, I multiply. So we all agree with negative 15 here? Now, this is another thing that I do differently. I like to put a little box here because this last piece is going to be our remainder from the division. Okay. This one comes out to be 0. What's problem here? Right? Can't deal with that, right? This is what we call an indeterminate form mathematically. So whenever you have zeros infinity mixed, as you can see here, 0 over 0, infinity over infinity, we're going to call this an indeterminate form. I can't really do anything with it. Okay. With that said, if you've taken a calculus course before, don't bring stuff in here from that class that you've seen before. We're not talking about that. So if you do that on a test, or if you go look up online how to deal with this, and you bring in something dealing with L'Hopital's rule, you will not get credit for it on my test. Is that clear to everyone? With that said, how do we deal with it? Well, what should I try to do to that quadratic?
Can we simplify it?
But that's what we're working towards. What do I have to do with the quadratic though to simplify it? I think so. No, not quadratic form, just factor it though. Right? The good news is this is why I like synthetic division. If you do synthetic division, the remainder is 0, guess what you have? You have the factors. Right? So this is where we would go into that next step and say, hey, let's try to simplify this rational. We'll have x minus 3 on top, but guess what? Based on what we just found, we have x minus 5. That's where I'm getting that from. And this right here is our other factor. The idea is, though, remember that we're going to put this as x minus 3. Okay. The reason I put it with the opposite sign, though, is what would this be if I plug in a 3 here? It'd be 0, right? So understand that we change the sign when we go to the factor, because if I plug in this 3, it would make that factor equal to 0. Okay. That's why I like synthetic division, though. You can do a quick evaluation just to see what's going on up here. But this is, again, what we call an indeterminate form. I can't do anything with it. But it also sets me up for factoring. For the quadratic, it's nice because it just gave me my factors. I didn't have to do all the other stuff, grouping, whatever it is you're comfortable with, okay? It is overkill for a quadratic, but since we were just evaluating, it kind of works out nicely. That's the idea, okay? Everyone good with where I'm getting that from? The work? Well, no, because you might do it differently. If you go straight to factoring, if you plug it in, you're like, hey, I see I could plug this in and get 0, and then you factor it, that's fine. So the key is when there's steps that, like, say you don't do that, you're kind of skipping just a little side work is all you're doing. Just make sure you're consistent in that, so that way when I go through your work, that we're not losing points for something that, like, you made one small mistake and I have no way to trace it. That's the concern, okay? But at that point, that's side work. I wouldn't say, even like here, this is something you could have put in the calculator, for goodness sakes. Is everyone clear on that? You could have typed that in the calculator to see if it worked. I just put it on there to make sure to show like, hey, all we're doing is evaluating the function to get that value. Here again, you could have put this in the calculator, right? Just plug it in here and get it. But hopefully what you saw, the reason I like synthetic division, it did two things for me at one time. It evaluated it to where I was like, hey, I got 0, so that's why I put 0 here. Everyone follow me on that? But then it also gave me the factors. That's the only reason I like to do it. So you'll see I'll do synthetic division a lot in this course as we deal with different things, okay? Only if the remainder is what? 0. Only if the remainder is 0. If the remainder is not 0, then we wouldn't even have to bother with it, because we would have 0 over a, whatever number it is, which is just 0, okay? But please understand though, like hopefully everyone heard that. Just because I write it a certain way, if there's another way that you like to do it, that's perfectly fine, okay? Just be consistent in your work and know that if I can't find bridges for partial credit, it's harder for me to give you more points, okay? So just make sure you're consistent and you're able to explain what you're doing, okay? Now, what do we like about this now that we factor? That was the last thing,
So,
right?
we-
So
each other.
they don't cancel because they go to what number? They go to 1, right? They divide out. I don't like the cancel word, because what number would you associate with canceling something? Mm-hmm. But now we get to this point here. And what can we do now? What can we try again? Yeah, let's try direct substitution again, right? What's 3 minus, oh. Sorry, let me know when it's off the screen, y'all. I updated my app and it's acting weird. Once I get here though, no, this is just, let me try direct substitution again. If it doesn't work, then we have to go and do something different. Please understand that. It could give us the indeterminate form again. The good news is what's in the numerator? 1. So at that point, that's helpful. But what's 3 minus 5? So our limit would be -1/2. Now, can I actually plug in 3 and get -1/2 though? No, so there's a discontinuity here based on the fact that we had to simplify to get this, but that's not what was being asked here. We were just trying to find the limit, okay? The limit exists though, and it equals -1/2. Now, hopefully what you see, what's the nice thing about direct substitution, right? We were able to find that the limit existed pretty quickly, okay? Any questions or concerns with this one before we look at some other ones? Now, the one thing I will say, and I'll try to make sure we practice more, is be prepared to have to go to a table approach. If you get stuck and you can't figure something out, a table will always work, right? If it approaches a nice number, of course, right? Sometimes it might be something you're like, I'm not really sure exactly what's going on here, but it will give you at least an approximation, okay? If you do a table approach and your answer was supposed to be 13 over 19, but you give me a decimal place, is that 13 over 19? Probably not, but approximation is better than nothing. Everyone follow me on that? With that said, like if you got stuck here and you weren't thinking about factoring to simplify, you probably could get to I'm pretty sure we get close to -1/2 through a table approach. But that would be a lot of work having to plug into those things over and over again. So be comfortable with your calculator, okay? That TI-30, you could plug that whole thing in and keep using it over and over again. Right? So if you want to learn how to do that, let me know. I'll go talk to my colleague that taught me how to and see if I can remember. Okay. But we do need to look at something real quick. This is more just kind of an overview. Please understand that we're going to get to situations where other types of discontinuities come into play, right? The nice thing I looked at, we had that removable one where we were able to do the limit. We just couldn't plug the value in because of restrictions. Okay. These situations are going to deal a lot with what's going on from the graphical perspective. So this is where a table might definitely need to be considered. Okay. Hopefully what you see here though is we have 2 over x plus 2 on what number are we trying to find the limit as x approaches? -2. What's wrong with -2 though when we try to do a direct substitution of that? All right, we would get 2 over 0. That is, I can't do that mathematically, right? This is, do not do that. I need to look into this further. So to look into it further, what did I already have set up for us? What am I doing to look into this further? I'm breaking it down as a left-hand perspective and a right-hand perspective. Does everyone see that? This is a situation. Keep in mind, the previous one was 0 over 0, right? So we said, hey, let's try to simplify and then see if it works, which thankfully, that one did work, right? I set it up to where that's what happened. But understand that's not always going to be the case. As we see here, I get in an undefined situation where, hey, I can't do anything with 2 over 0, so let's break it apart and look at the left and right-hand side. Okay. With that said, we still can't do direct substitution because it still would be the same thing. So this is where, looking at the graph, but in our case, we don't have the graph. To get the graph, we'd have to plug in points. So let's just build a table. All right. So as we build this table real quick, what I want you to see is that we can kind of do it quickly. And this, again, being comfortable with your calculator is going to be helpful. But as I deal with this particular one here, we'll call this g of x, just to make it a little bit easier to write out in the table form. What numbers should I put here to help me understand what's going on from the left-hand side? What are some good values? -4, I like -4, right? Because -4 is less than -2, right? And you said what? Positive or negative? -2.5. I like that one too, because we're getting a little bit closer now, right? -4 is a good place to start. -2.5 gets closer. What's another good one then to get it even closer? I want to do 2.9 now, not -3. I would do -2.001, right? Those are good numbers if we were on the positive side. Okay, so understand here, 2.9 would take us further away. -3 would take us further away. Here we started at -4 and we're getting closer. Then we want to get a little bit closer. Okay, so this is where sometimes maybe writing out the number line so you can see the values might help you a little bit. Okay, now I'm going to put these in my calculator real quick, but if you do -4, we should get what? -1/2, -1, sorry. We do -2.5, what is that negative? Oops. That gives us -4. And if you want to write these out when you do them, that's fine. But just to do them real quick, what is something that you noticed happened to the number, especially when we went from that -2.5 to -2.001? That's -2,000, right? The first two from -4, -2.5, it decreased, right? But not necessarily by a lot. It was just -1, -4. The second I went from -2.5, -2.001, it jumped up a lot, right? Let's try looking at it with 4 zeros, just to kind of perspective to see what's going on, okay? So all I did is changed it by, we're talking, what's that, 10 thousandths of a amount. How much did it change in the output? It went from -2,000 to negative what? 200,000. At this point, what do you think it's going to do? The closer and closer we get. If we keep putting more zeros there, what do you think it's going to do? It's going to keep increasing. What number could we use, or mathematical symbol in this case, could we use to represent the fact that this is just going to keep on growing and it will not stop? It is infinity. Now, keep in mind, though, I started to give it away. This would need to be negative infinity because all our values are what? Negative, right? So keep that in mind. So understand there's gonna be times where our limits can spit out negative infinity. At that point, you know, continuity wise, there's an alert going on. I definitely probably have a discontinuity here. In this case, we should be thinking asymptotes. Right? What should I expect from the other side? Probably a similar pattern, right? Is that always going to be the case? It depends on what we're working with. In this, we can assume that it probably is going to be the same thing. Now, the key that we need to look into though, is it going to be negative infinity or is it going to be positive infinity? That's what we want to do. So if we do this real quick again, before we finish up, we're going to take that same approach, but this time, remember, we're going to the right side of -2. So I would do -1, -1.5, -1.9, and then let's use 3 nines. Keep trying to get as close to -2 as I can without actually plugging in -2. What you're going to see here is that we'll see kind of a similar pattern, but what numbers are we going to get? Positive numbers. Huh? What were you going to ask?
Is that's not supposed to be?
Yes, because we're still approaching -2, right? Now, could you plug in a positive number? Yeah, but hopefully you see, I just want to get close to -2. So there's no point in plugging in like 5. It wouldn't necessarily help us much. This is one of those things where, like, understand, we're not looking at the whole domain of a function. We're kind of trying to zoom in on a particular value. Nothing was wrong with -4, but as you can see, I just picked -1 right off the bat here. It's like here, I might have picked -3 to start myself. Nothing was wrong with -4, but like if you would have said 5 first, I would have said, hey, nothing's wrong with 5, but let's try to keep it a little bit closer, right? Now, just doing those values here, do you feel comfortable seeing that it's going to grow pretty quickly the closer we get to that value? All right. So would we agree then if I put a positive infinity there? What would you conclude about the limit? Are those the same? Oh, one's going down and the other one's going up. Keep in mind, these are y values, right? So negative infinity says my graph on one side is doing this, while on the other side, it's doing this. I don't have all the details. We could plug in points and use these to graph it if we wanted to now. But remember, that's where we talked about, hey, I actually have this thing called a vertical asymptote on this graph that I could have talked about. And we'll look at that a little bit more too, as we discuss these limits a little bit further. But I have a vertical asymptote here, right? So this being the fact that they're both different though, remember that's the key. If they're both different, we would say limit does not, limit does not exist. Or D and E. All right, we looked at the left hand, we looked at the right hand, they're not the same. Limit doesn't exist. Okay. Now, it's all we have time for today, but what you'll see is I want to continue practicing some limit stuff. We're going to start bringing in the rates of change, how that impacts and how we use limits there. Note also though, as I look at infinity being an output, we could also talk about what happens as we approach infinity, right? This would be another good table one that we can look at from a table perspective. Okay, so just know that's where we're going as we move forward. Any questions as we finish up today?